Hello everyone, welcome to Electronica 2020 to session 3 of the Embedded Forum of IoT, Connectivity and Security. Today at Nexperia we'd like to present ESD Protection, why it is important and how it ensures safe operation for connectivity. My name is Lukas Droemer. I'm the responsible product manager at Nexperia for Automotive, ESD Protection and EMC. I'm located in Hamburg, Germany.
My name is Andreas Hardock. I'm application marketing manager also in Hamburg, and here I support the ESD portfolio from the technical point of view.
IoT and increased connectivity are no longer any buzzwords. I assume everyone is using a smartphone on a daily basis. Andreas and I are using a laptop right now to record this webinar. But those new technologies are affecting us much more, whether it be in smart homes, in smart cities, or in smart vehicles. We all have our touch points with this new technology and how we engage with it. When it comes to mobility and the automotive world, we see mega trends like autonomous driving, electrification, but also the shared mobility, changing our way we interact with automotive world. It was once Henry Ford who said, "You can have any car if it's black." This statement is no longer applicable. Our expectations to vehicles change rapidly. We want to interact with our vehicle via a smartphone. We want to enjoy keyless entry. We want to enjoy smart engine control, etc. As such, expectations are rising. In the end, it means we have to work with more data and have to transmit more data. And in effect, the current setup we have in the car and the in-vehicle networks is not sufficient anymore. This flat architecture is cost intensive, and it's also not very reliable to the requirements in the future. And as such, we have to move on with a new wiring harness, with a new concept how to wire a car, and move on to the domain architecture, and in the future even more to a zonal architecture where we have the central computing platform. As such, developing a service-oriented architecture in the car, we actually can realize our expectations to autonomous driving. As such, we can achieve a level 5 of autonomous driving, and we can establish the car more and more to the all IP car, establishing out the software in the car more. Software is key to work with the data, to learn from the data, and for instance to teach ADAS modules. But without the right hardware, we cannot process the data. In the mobile world, we know, of course, the trend of the Moore's law, how feature sizes are shrinking. The semiconductor content on the PCB is increasing. The density on the PCB is increasing even more and more. But in mobile, we're also working with low voltages. The quality requirements are way lower, and also the operation lifetime of a mobile device is from 1 to 3 years. When it comes to automotive and those mega trends of increased connectivity, autonomous driving, electrification and shared mobility, the requirements are much harsher when it comes to ICs. So also here, the component density on the PCB is increasing, and also the feature size of an IC is shrinking. But we have to handle much higher voltages. So for the electrified car, we're talking about mild hybrid or the 8048 volt board net. So the voltages are much higher that need to be handled. But also here we have much harsher temperatures, ranging from -40 to up to 175 degrees on the board itself. But also the operation lifetime is much longer for a car, ranging for a minimum of 10 years, 15 years, or even longer. Always under the aspiration of having zero failure. So as the in-vehicle networks setups or the new protocols shape the requirements to ICs, the new IC requirements increase the threat of ESD. In the graph, you see on the y-axis the gate thickness of the feature size of the IC, and on the x-axis you see the relative ESD design costs. And now we have to picture some IC areas, which are the gray boxes, and then you see those red boxes, which show the ESD area on chip that is needed to achieve 2 kilovolt human body level robustness. This is the standard value for assembly or production device level robustness. And what you see now is that if we shrink the feature size more and more, the ratio of the ESD space versus the feature size is actually flipping. And if we come to a level of 2 nanometers or even lower, we see that we would need even more ESD area on chip than the feature size itself to still achieve 2 kilovolts human body model robustness. And this is just crazy. So the relative cost of ESD increase exponentially, and this is really a challenge for you design engineers, because the IC robustness will decrease more and more. So we need a way out to avoid those increasing costs here. And luckily, discrete ESD solutions provide a new concept how we can get out of this downward spiral and have a smart approach to solve this problem. So ICs become more and more sensitive, and the relative design cost for ESD is increasing. But what is the problem with ESD? ESD is the abbreviation for electrostatic discharge. It describes a sudden discharge event between persons, devices, or components. It's a triboelectric effect that can occur anytime and everywhere. The problem with ESD is that it's causing this malfunction and really destroying on a micro level. On the pictures here, you can see the gate oxides, metallizations, or PN junctions of ICs and other semiconductor components. And you see how this discharge is really causing this micro level damage. And this is something which we cannot accept when we focus automotive, but in general, despite of mobile computing, automotive, industry areas, ESD damage must be avoided because we cannot detect this malfunction, we cannot detect this micro level damage in components. And if we handle much more data on a higher speed, we want reliable systems. So when we want to have reliable systems, it is a question of perspective when it comes to ESD. If you look on the whole application, the PCB, this is called the system level perspective. So here the ESD can really damage the whole application, and that's what must be avoided definitely. There are norms and standards that represent the system level perspective for ESD. So for instance, the IEC 61000-4-2 or the ISO norm 10605 for automotive. The system level is the key perspective we have to take as the design engineers. But as shown before, 2 kilovolts human body model describes the device level of an IC itself. So here we have to distinguish on the on-chip protection and the ESD robustness of a device itself. And this can be represented by the human body model or the charged device models. And this describes only the ESD robustness for assembly and production, etc. But it gives no indication on the system level robustness itself. So when thinking of ESD, we will always have to distinguish between those two perspectives. But ESD is very critical on a system level, and that we will show on the next slides.
Here we see an example which is showing us the difference between the device level and the system level robustness. For this, we have chosen a CAN bus network, which you can see on the right side. This is containing of a CAN bus transceiver, a common mode choke, a termination, and the ESD protection device, which is placed directly at the connector. This placement we always recommend. In the case of an ESD event at the connector, the ESD protection device is triggering and taking the entire amount of ESD pulse. In this case, the system is protected by far the best. Without an ESD protection device, the ESD energy is taken by the CAN bus transceiver. Here we have the less ESD system level robustness. On the left side, you can see a table which shows you real numbers of the system robustness. Here we have tested several CAN transceivers, and you can see that without an external ESD protection device, the ESD robustness is only up to 12 kilovolts maximum. By placing an ESD protection device here directly at the connector, we improve the system level robustness up to 30 kilovolts. Again, this is an example for CAN. We can show clearly that also for other networks, the system level robustness will be clearly increased by using an external ESD protection device. In order to have a proof of concept and also in order to visualize an ESD event on a PCB, we are using an EMI scanner. This is a nice tool also for failure analysis. You see on the right side the entire setup, also including the pulse generator. With this setup, we can analyzing the magnetic fields and with this also the currents on the PCB. And we here can also identify how much an external ESD protection device can improve the system level robustness. Here we see a result from such an EMI scan. We have taken a video and we are showing here only some screenshots. For this, we have chosen a CAN network as an example, which you can see on the right side. We investigated two scenarios. On the left side, you see the scenario without having an external ESD protection device. The blue color indicating a low current density and the red color is indicating a very high current density. And you can see very clearly here that a lot of current is flowing into your IC and causing a potential damage inside of the IC. In comparison, in the right figure, you can see the scenario with having an external ESD protection device. And in this case, we see that at the IC, only very less current can be observed. The entire ESD pulse is taken by the ESD protection device, which is placed here very close to the connector. You also see that all this ESD current is flowing in the ground layer, which is indicated in the upper figure.
It became clear that ESD protection is essential to ensure safe operation of a system and ensure good connectivity. And as shown in the entry of this presentation, the connectivity and the protocols of the car are evolving. And as such, we have different protocols for low speed, like the LIN and famous CAN bus. We're now talking about gigabits for Ethernet. For SerDes, we have 12 gigabits per second. And for the infotainment, we are even going higher up to 20 gigabits per second. And with these different speeds and different kinds of protocols, we also have different requirements when it comes to ESD protection itself. And that's why we at Nexperia clustered our ESD portfolio to those different application groups and shaped a portfolio where you can find the best system level protection enabler for each class.
Besides the examples we have shown you here, there is a lot of more to cover and to think about ESD for every one hardware design engineer. Therefore, Nexperia created an ESD application handbook especially for automotive application. Here we cover a lot of fundamentals and principles of ESD and ESD protection devices. We also explain the data sheet parameters and how the ESD protection devices are tested. We also show what are typical failure symptoms and failure mechanism caused by ESD and by surge event. We then cover the selection, how to choose the right ESD protection device for all automotive interfaces such LIN, CAN, Ethernet, and also infotainment, LVDS, USB, and HDMI. In addition, we also explain how you can improve your system before testing by using ESD simulation methods. Here we have the SEED, the system efficient ESD design, in order to test your system and to improve it before the first PCB is done. We also cover EMI filtering with common mode filters.
Besides the ESD application handbook, Nexperia offers you a lot more of information material. If you visit our webpage Nexperia.com, you will find the whole Nexperia portfolio ranging from diodes, transistors, ESD protection, MOSFETs, and logic devices. We have also a very handy tool called the parametric search, where you can narrow down the electrical parameters and also packages and have the selected portfolio for your application. You will also find a lot more application notes, leaflets, and other recommendations in order to choose a discrete semiconductor device. And if needed, we also offer a lab support where we can help you with our dedicated engineering team to support your requests and give you more guidance on your system level design. And we can help with tools like showing the EMI scanner, but also with simulation, for instance, the SEED, System Efficient ESD Design, Skeleton Parameters, or SPICE models. And for now, thank you very much joining our presentation here. And of course, you will find our contact details on the booth side, but also more information on Nexperia.com. Thank you very much.